Welcome to the PLC Professor's Workshop and Development Lab. This is where we sort it all out. I have another location where I strictly do text work. But in this location, I work with the equipment and with the software to make sure that the labs are as good as they can be. Now, what we're going to do today is talk about the virtual machine. One thing that I've done or tried to do is when I go from, we'll call it RSLogix500, which is SLC500 MicroLogix, MicroStarter Lite. When I go from, we'll call it the SLC500 MicroLogix realm to the RSLogix500 Studio Logic Designer, and then to CCW, the Micro 800, I try to use the exact same applications and lab projects because a controller is a controller. They all function relatively the same. What's different is the graphical user interface, and some of them have features that the others don't. But the examples in the lab projects are, in my estimate, the best that I could come up with that demonstrate the apparent nature of instructions and the unapparent nature, as well as scan order and other functions. So this virtual machine has been around for better than 10 years. It's been in every single thing I've done. It's the last final large project. And it was originally developed with 6 inputs and 4 outputs because my first go at this was with a RSLogix500 10-point I/O that has 6 inputs and 4 outputs. Then I started to expand it, and that's when I realized that when you're executing one of these projects and you're using one of these digital field device simulators, whether you're using mine or yours, it's just a box with 6 inputs and 6 outputs. What I learned was it's hard to keep track of which switch is which and which light is which. So we don't want too many I/O involved. However, with CCW Micro 800 and the simulator, it's given us some new opportunities that we don't have necessarily with 500 and 5000. But what we're going to do in this lecture is we're going to talk about the virtual machine, all the ins and outs. We'll talk about the actual hardware too, cylinders, motors, conveyors, sensors, barcode reader. So we're going to talk about all the elements in this virtual machine or process. If you find sections boring because you already have that knowledge and familiarity, well, just fast forward or drag the progress indicator along until you see something that looks new and then continue from there. So let's have at this. Virtual machine process. This is a PLC University lab project, and it can be found in any of these 4 manuals. The first one is the only offering that we have for the RSLogix500 realm, but the lab projects in this manual can be done with a SLC500 or any MicroLogix. This project or this machine we're going to discuss is the last and final main project in this manual. And then the second programming examples, RSLogix500, Studio5000, now called Logix Designer. This is 1 volume of a 2-volume set, and it's you could say the second half. This also has this project in it. The Connected Components Workbench with the Micro 800 uses this same machine as well. Now there's a second and a third edition. So actually, even the first edition has this lab project. So if you have any of these manuals, then you have this lab project to use. And as I said, as we go through this, if you find something is boring, just fast forward. This graphic should be recognizable by you because it's in your lab project manual. And if you don't have the manual, you need to get it. Otherwise, there's not a lot of sense to spending your time watching this video. And in the graphic, I have laid out the steps in sequence for this machine operation. The general idea here, and I'm not going to go through all these steps in this graphic, but we have raw stock that comes in from somewhere upstream in the manufacturing process. Now, when I say upstream and downstream, obviously I mean things come from upstream and then they exit downstream. In this case, they can exit off of conveyor 1 or conveyor 2. If this particular component or raw stock does not require a hole bored in it, a drill bit run into it, then it's going to pass right on through and out M1 to whatever the next process is downstream to the south. However, if the barcode reader, when it reads that code, if the PLC says, oh, I need to bore a hole in that, it's going to, and by the way, PE1 triggers the barcode scanner. That part will continue down until it hits PE2. Cylinder 2 will extend and push it into the workspace. Now, cylinder 1 with stop 1, that's there for you to use to block any additional raw stock that is coming from upstream if it's too early. If it's arrived too early, you want to stop and hold it there. So cylinder 2 pushes the part into it clamps it into the boring station, and then the drill motor starts up, gets up to speed, and then cylinder 4 extends, pushing the drill bit into the part. Once it's all the way into the part and through to the center area or the depth for the hole, then it stops for a moment, pauses while it augers out the debris from the hole, and then cylinder 4 retracts the drill motor with bit back out, and it may or may not continue spinning to make it cool off faster. It just depends upon your production rate. Then once all the cylinders are clear, I mean, you have to retract cylinder 2. Once you pull the drill bit out, then you retract cylinder 2, and then cylinder 3 extends and pushes it onto the finished product conveyor, conveyor 2. And then once it's on that belt, it can either sit there, or if it's not wanted downstream, meaning off the end of conveyor 2 to another machining station or packaging, then stop 2 may extend out, and then when the conveyor starts up and it moves it from the PE4 position to the PE5 position, then the conveyor stops. We don't want to leave the conveyor running with the part stationary and have it scuff the bottom of the part. So that's kind of the long and the short of it, without going through all the individual steps. PE1 senses part, number 2 barcode is triggered, it reads a barcode, and if that barcode says, yeah, this needs bored, then number 3, PE2 senses the part, and then cylinders 1 and 2 are going to extend, and so on and so forth. And I have the proxies in there. So the inputs are more or less in cyan, bluish, cyan, and the outputs or the actions are more or less in orange. And then, of course, the final one is 19, step 19, cylinder 5 extends. So now let's talk a little bit about the actual components. So when you look over this system, it's really pretty simple. You've got 5 cylinders, 1, 2, 3, 4, and 5, and you've got a drill motor, and you've got 2 conveyors, and you've got some sensors. Okay, how do we make things move? Well, cylinders are our primary element of motion, and they are 2 position, retracted or extended. Now, this is a typical construction of a cylinder. Now, whether this is hydraulic or pneumatic, we don't care. There's a barrel with a piston rod, there's a rod end, and a cap end, and then each end has a port. In this case, and remember the barrel's most likely aluminum, so there's a magnet that moves with the piston, and that magnet is there to be sensed by position sensors. Notice the 2 ports, and I'm going to try to give you more than you need to know, and you can just ignore it if you want. But when you look at that piston, there's the cap end side, and we usually call that the piston side. And then there's the rod end side, which you can see. You can see the rod attached to it. Well, let's say that the piston end, the side you can't see, that's all the way up against the cap end, let's say that's 3 square inches. And you apply 50 psi of air pressure. That's 50 pounds per square inch. Well, with 3 square inches, that's 150 pounds of force when the rod extends forward. But then when you retract it, notice that some of the surface has been reduced by where the piston rod attaches to the piston. Now let's say that's 1 square inch, thereabouts. That means you've got 2 square inches left of surface for 50 psi to push on. That means it's going to retract at 100 psi or 100 pounds force. It extends at 150, retracts at 100. That's just something to keep in mind, folks. Also, typically these cylinders have something built into each end called cushion. And what that is when it reaches the end of stroke, within the last quarter inch, we'll say, there is a chamber and something on the rod and piston that interferes with that chamber to reduce the flow. So it comes to a softer stop at the end of stroke on both ends. Now you don't need to know that to work with this project. I'm just throwing in a few extras to try to make it more interesting. Okay, digital motion sensing means that we want to sense the position that the piston is in. Now, we might say cylinder, but we mean the piston. So the piston has a magnet on it, and these sensors are most likely Hall effect, H-O-L-L, Hall effect. And here's what Hall effect is. If this image that you're looking at, this rectangle, were a piece of copper, and you were passing current flow through it from left to right, typically it would spread out fairly evenly across the whole strip of copper. Or if you want, say this is the wire. Typically you're going to have more electron flow in the center of the wire than towards the outside, simply because of something called counter EMF, counter electromotive force. In other words, the magnetic field from the electrons traveling all one direction in the middle of the wire, as that field expands out, it opposes the electrons further out in the wire. Okay, so let's get back to this Hall effect. So you've got electrons flowing through this conductor from left to right. If a magnetic field, stationary magnetic field even, if it is moved in where the field has an influence over this conductor, then the magnetic field will encourage the electrons to go to one side or the other of the conductor. What that means is that from, not lengthwise of the wire, but the sides of the wire, one side is going to be kind of negative and the other side kind of positive. Add a little bit of electronics that can sense this difference of potential, and now you have something that can sense when there's a magnetic field that is influencing this conductor. That's a Hall effect. And you can see they slide into slots, and then there's a little set screw. This graphics resolution is not that great, but the little dark circle in the orange, or maybe it's in the black, but it's a set screw. You loosen it, you put the piston in the position you want to sense, and then you slide the sensor until it sees the piston. Keep in mind that there is some hysteresis in this adjustment. You would not want to move the piston all the way to the rear, retract it, and then push the sensor forward until it just misses or just catches. You want to give a little bit more space than that, because there is some hysteresis. Now this is another example of a cylinder with a rod, a piston, and it's got 2 sensors. These sensors clamp. You loosen up the clamp and slide it along the barrel, and that's how you adjust to detect the position of the piston. Real simple. These things work really good. Now in some cases you'll have processes where the cylinder is so short, the stroke is so short, that you can't get the sensors in the right position, meaning that they run into each other. And I've had that happen. In that case, what you get is just one sensor, and typically you detect the retracted position, not the extended. That's because you want to know for sure that it retracted so it's not colliding with other components out in the workspace. And then you're just going to have to use a little timer to say after 1 second, we're assuming the cylinder extended, and it's a time-based event instead of a actual true event where something actually happened physically. Now there's a couple other features on this cylinder worth mentioning, and that is the ports. Notice there's an elbow on each port, and each of those devices has a fluted turn wheel and then a nut to lock it down. So this is how you adjust the airflow. So these are flow controls. Now this is one that's more or less like what you're seeing. It's a 90-degree elbow. Notice on the side of it, you have two symbols in parallel with the thread on the bottom of the symbol. What looks like a capacitor with an arrow through it, that's the adjustment. That's the flow control. The other thing is a check valve. Now if you think about the ball and the seat is on the top and the ball is on the bottom, which means when air flows from the bottom, up through the threaded part, it's going to close the check valve and all the air will be forced through the variable adjustment, okay? So that means when the cylinder is exhausting the cap end, that is where the flow control takes place. When air is coming in this fitting, and by the way, our nice fitting there is threaded for a national pipe thread. The one on the cylinder is a press-in tubing with a release. I'm sure you recognize this stuff. So when pressure is applied to the device on the cap end, it opens the check valve and goes into the piston or the cylinder freely. So just remember that you are always adjusting the flow control on the exhaust side. If you don't know that, then you're going to do it backwards and wonder why nothing's working out right. Okay, this is another picture of the same thing. Notice it has the same two symbols on it. It has what looks like a variable capacitor. That's the flow control. Then you have a check valve symbol. This kind attaches to the frame or the fixture instead of directly to the cylinder. The ones on the cylinder I kind of like because they're easy to find. The other one, who knows where they're going to hide it in the plumbing. Okay, so this is what we're looking at here. We have a piston, a cylinder, we have a rod and something on the end of the rod, and we're sensing it in the retracted position, which we're calling home. As you apply pressure on the cap end, that's going to push the piston, push the rod, and that object detected by the proc switch home, it's going to lose that presence and eventually it'll show up at the end. These two sensors are detecting end of stroke or two positions and are doing the same job that those other sensors did. Personally, I would rather detect what you're moving than detect the piston, because the piston can move and what you want it to move didn't move simply because it's disconnected, broken, or something else. Personally, I prefer using proc switches or photo eyes that actually detect the location of the object that I want to determine where it's at. It's okay if you do the cylinder ones, that's an easier install. Obviously, if you're going to do it this way, you have to have some place to attach brackets for either a proc switch or a photo eye. Okay, this is another type of position sensor. This one's analog, and this sensor senses the entire length of the stroke. So you notice down below on the cylinder housing it says stroke and it shows a blue dashed arrow. So that's the total travel of that piston. Okay, that sensor up there puts out an analog signal 4 to 20 milliamps or 0 to 10 volts that is proportional to the distance that the piston is from one end to the other. So typically you would teach it for one end, because remember, you don't always go to the end of the stroke on the cylinder to reach the end of the motion of the piston rod. In other words, if you got a 3-inch stroke, you may only use 2.5 inches. You retract it to the full retract position, or maybe not. In some cases, you might have 5 inches of stroke to use, and you're only using 3.5 inches, and neither position is all the way extended or all the way retracted. So this sensor puts out an analog signal proportional to the distance that you trained it with. And these are some examples of this sensor. So obviously, if you're going to use one of these, you need to buy one that's got more range of travel than what you have stroke, just to make sure that you can put the whole stroke inside the range of this sensor. Naturally, these are more expensive than the Hall effect sensors. How do we move that cylinder? We move it with a solenoid valve. And what you see here are two diagrams, and this is a two-position valve. This could represent hydraulic or pneumatic. As a matter of fact, the T on the symbol is tank or reservoir. And on a hydraulic system, you don't dump the exhausted hydraulic fluid out onto the floor. It goes back to the reservoir. But with an air system, it goes out the exhaust and joins the atmosphere and all its buddies out there in airland. Okay? So T really could be exhaust, or you could say reservoir if you want to look at all the airspace around you as the reservoir. Now that symbol down there has two squares. Okay, and the one to the left shows AB on top and PT on the bottom. And how you read this symbology is in one position that P pressure goes to B, a port on the cylinder, and A on the cylinder goes to T, tank or exhaust. If you shift the spool, then the square on the right-hand side shifts over, and now P goes to A and B goes to T. And that's what you see up above. So you see the spool is that rod traveling horizontal that has the two, if you want to, kind of reminds you of camshaft lobes, but they're not eccentrics. They're bored extremely close tolerance. As a matter of fact, some of these pneumatic valves have O-rings to seal those lobes on the spool. Some of them have a micro finish, meaning that the tolerance is so close that it's metal to metal when the spool is shifting. So you can see the symbol on the left hand is pressure goes to B, and then as the piston moves, it pushes air into A and out T on the bottom or exhaust. If you shift the spool the other way, now pressure is going into A, coming out B, and going to T or exhaust. That's a two-position valve. Now, you can use two solenoids to move that spool. You can have a solenoid on each end. Energize one, it pulls it that way. Energize the other, pulls it the other way. Of course, you have to make sure you don't energize both of them simultaneously. That's why in my logic, I always have conditions that will not allow you to extend or to energize both solenoids simultaneously. Now, there's also detent solenoid valves, meaning that you pulse the valve, the solenoid, and it pulls it to the right, and then you de-energize the solenoid, but it stays there in a detented position. And then when you want to go to the other position, you pulse the other solenoid and it pulls it back in that position, and they then detents it. There's also single solenoid, and with a single solenoid, you've got a at-rest position, and I'm not saying that this is at rest, but this is one position, and when you energize the solenoid, it moves the spool from left to right, and then you have the other path shown, and vice versa. Okay, so I'm just showing you how to read these graphics. Now, a single solenoid valve only has one solenoid, and that's indicated by the little rectangle on the right side that has a little arrow on it. That's electrical. On the other end, you see the symbol for a spring, so it's spring return. So the solenoid, electrical solenoid, shifts the spool in one direction, and when you de-energize the solenoid, the spring pushes it back. So that is a single solenoid, two-position valve. And you can tell by looking at the symbology there that right now pressure 1 is going to 2. That's the B side of the cylinder. Then the exhaust from the cylinder is coming in 4 and out 5, the exhaust port. If you shift over that symbol, the whole thing to the left, now you've got pressure going to 4 and 2 going to the other exhaust. So you see down 3 and 5 are both exhaust. So one's open to A and the other's open to B. And when one opens, the other one's blocked. It has like a little T symbol. Okay, now this is a 2-position but double solenoid. Now I'm using the same photo in this and the next couple slides just to remind you what a double solenoid valve looks like. However, the symbology on the side of the valve will not match. As a matter of fact, if I look closely at the symbol on the actual photograph where it says Nitra, AVS, whatever the part number is, that is a 3-position double solenoid, not a 2-position. But you wouldn't know that unless you looked at the symbology on this actual photo of the valve. So let's just pretend that the symbol on the side of this valve matches what you see to the right. Okay? Now the only difference between this and the previous symbology was this is a double solenoid instead of one solenoid and a spring. So instead of energizing the solenoid, shift the spool, de-energizes, and the spring pushes it back, you are using an electric pulse or power to move it to and maintain it in one of these 2 positions. Okay, now we have something, a symbol to the right that is closer to what's on the left. Now what's on the left, notice it's got 2 solenoids and 2 springs. Now I mean, both the symbol does to the right and what's on the side of the valve. The only difference is that the center configuration, in other words, if you look at the side of that valve real close, you'll see 3 squares. You've got pressure going to A, B going to exhaust, and then on the far side, you've got it just opposite. And then in the middle, you got 2 arrows going straight down. That means that both A and B ends of the cylinder are going to the exhaust. That means that both sides of the cylinder, the piston side and the rod side, they are connected right to the atmosphere, which means you could move that rod back and forth with your hand. There's no pressure holding it. Whereas the symbol to the right in our slide here, that is closed center. It's 3-position. You know, in one position, you got pressure going to A and exhausting out of B. And then at the far end, you've got it just the opposite, pressure going to A and exhaust coming out of B. And then the other end is pressure going to B, exhaust coming out of A. But in the middle, remember you got 2 springs. So when you energize one of these 2 solenoids, it's going to pull it to one of those end configurations. When you de-energize it, the spring pushes it back to the middle square where all ports are blocked. The exhaust ports are blocked, the pressure is blocked, and both A and B for the cylinder, they're blocked. Which means that the cylinder has that pressure trapped on one side and it more or less keeps it from moving. So 3-position closed center. Remember, I'm telling you more than you need to know for this virtual machine, but why not? Okay, 3-position exhaust center. Whereas this one, when its spring returned to the center position, remember this is 3 positions, then all ports were blocked and the exhaust are blocked. So it holds pressure right where it's at. And which side of the piston it's on depends upon which one of those solenoids was energized before its spring returned to this position. This one has both sides of the cylinders applied to the exhaust. Here, it's blocked, so the air is trapped. The pressure is trapped in the cylinder. This matches the actual diagram that's on the photo of the solenoid valve. And that's, as you can see, A and B both go to exhaust when it's in the center position. And then, of course, if you energize a solenoid, it pulls it over, and you've got pressure going to A, B going to exhaust. And then if you remove the energize, you de-energize the solenoid, it goes back to the center, and whatever side had pressure on is going to exhaust to the atmosphere. Then if you energize the other solenoid, then it puts pressure on B and A, or on A and now B exhaust. You can see, I think you have an idea now of this symbology. It's really pretty easy to read once you get used to it. Okay, and this is a 3-position pressure center. This is where you trap the pressure on both sides. So you may think that this is the same as blocked like that. In other words, if we put pressure on A from 1 to A, 4, and then let a spring return to center, then the air is trapped on the piston side and the rod end is all the way extended and it's held there. And that is true. This one holds pressure on both sides. So the pressure is distributed evenly from 1 to both 2 and 4. So there's many different configurations for the spools and how they route the air in these solenoid valves. Okay, here's a solenoid valve, and whether this is single solenoid, so there's no guesswork here on how it works. However, notice that the ports that were called T for tank or R for reservoir, what they have screwed into them is a combination flow control and muffler. Because remember, the flow controls are on the exhaust side. And I've got 2 images of mufflers combo flow control. These are nice. Now, these only work on valve bodies that are freestanding. If you happen to have this valve mounted on a manifold, different story. Now, if it's on a manifold, you've technically only got one exhaust port, so to speak, and you can put a muffler in that. And a manifold is where you see 2 or more valves that look like they're all bolted together side by side and mounted on a common metal plate about an inch or so thick. That's the manifold. And so you bring in pressure to one port and you have exhaust on one port. Then the manifold distributes the pressure and the exhaust out to the individual valves. Okay, the other movers that we have in our machine are conveyors. And this is a belt conveyor, and it's a slide plate belt conveyor. What that means is that the belt slides on a flat plate underneath of it. So any objects traveling don't stretch or deflect the belt downwards. But you do lose a little in friction on the belt against that plate. And you can see a 3-phase AC motor. Now, it could be 115 volt single phase, but that's unlikely, but entirely possible. Okay, so that's a slide plate conveyor. This is a roller belt conveyor, meaning that the belt travels on rollers with bushings or bearings. So there's a lot less friction involved, but it can be kind of bumpy if you have heavy, small objects because they tend to want to deflect the belt a little between the rollers. But both these conveyors do the exact same thing. They convey something from one end to the other. Now this is a live roller, no belt. And the product or the cartons move along these rollers because they're all driven by the electric motor. And you can see how it's configured with sprockets and chains. Now, the difference between the motorized rollers and the belt conveyor is that some things can slip easier on the metal rollers than they will on that rubber belt. Also, the shape is not as important on the belt as it is on the rollers. You don't want the parts kind of tipping down between the rollers. Another way to do the rollers, to power them, is with, well, I'll just call them rubber bands. They're polymer, round, stretchy pieces bonded together like a rubber band, and they run from roller to roller. So each roller has 2 pulley notches in it, and you can see that every other one, it's in the other notch. Now that's the one in the middle. The one at the lower left corner, you can see there's a drive line down below the conveyor. As a matter of fact, there's 2, and they're ganged together with a chain on sprocket. And the rubber bands, if you want to call them that, they are stretched and twisted 90 degrees from the pulleys on the drive rod and the, if you want to call them, the pulley notches on the rollers. So conveyors. Okay, electric motor. Now, This is a three-phase motor. I have some like this. Now this says three-phase 40 watts. Now you could calculate the horsepower. There's 740 watts in a horsepower, something like that. So you could do your calculations, but it's a small motor. It's got a gear reduction unit on it. So that square thing between the motor and the motor mount and sprocket, that is a gear reduction unit. So this is a three-phase motor. Any motor would have done for the picture. You see a sprocket on it. It could have a pulley, but for a conveyor it's probably going to have a sprocket because it's going to have a chain going to a larger sprocket to slow the speed down. So a gear reducer gives you a lower rotation at the sprocket than you have the shaft or the armature. Say three-phase motor. I use these on all my training VFD stations. Not this specific one. I use actually it's pretty close now that I'm looking at the label, but I use a three-phase motor that's a fractional horsepower, like 125th. But it is a three-phase motor, 233 phase. Okay, the motor is controlled by something that kind of resembles a relay. The reason this is not a relay, two reasons. One is when you get into larger current flows, they tend to call them contactors instead of relays. Plus, this one has motor overloads. When you look down at the bottom of it, you'll see a reset button and you'll see a tripped indicator. Well, this is a three-phase relay type switch. So you have power coming in L1, L2, and L3, and then out of the bottom you have three conductors going to the three-phase motor, T1, T2, and T3. You also have a motor overload relay, or if there is excessive current, it'll heat up a thermal type device that will open the circuit and it trips the motor overload relay, and you use that contact to shut off the motor. It also has an aux contact. You can see over to the left side, looks like a normally open contact with label 2 and 3, P2. That's a aux contact that you can use going back to the PLC to tell you whether the armature on this motor starter is energized or not. So this is just like an on-off switch for a three-phase motor. Now, if you want to reverse the motor, in other words, if you want your conveyor to go forward and reverse, then you need a reversing starter. And so what you see here in the middle is one of those gizmos, you know, the starter on the far left. I mean, it's not the exact same part number, but it's the same thing. So you see one of those, and then right next to it, you see the upper part of it, the actual switching part of it, minus the motor overloads, because you only need one motor overload relay for this one motor. So you have power coming in the top and going out the bottom. So you have two L1, L2, and L3s, and then you just have one T1, T2, and T3 coming out of the bottom. The motor starter to the far left, that's just on and off for that motor. And the speed of the conveyor is going to be 1720 divided up by the gear reduction between the gear head and the ratio of the sprockets going to the conveyor. It's just fixed speed. However, if you want to control the speed and the direction and accel and decel, sometimes you don't want the conveyor to start up with a jerk. You have acceleration settings and deceleration settings. This is a PowerFlex 525, one of my favorites. I use these on all my training equipment. You see in the middle, I have an image of it with the cover removed. You can control this drive and thereby the motor with discrete digital outputs from a PLC, those two terminal strips. They're gray, and then there's three that are orange, the safety. Well, you can do 2-wire, 3-wire, and other methods of control. You can also hook up an external potentiometer for speed control, or you can have an analog output from the PLC that wires in here for speed control, or up underneath the faceplate, the 4 blue buttons with one in the center. Right below it on that circuit board is an RJ45 connector for Ethernet IP. We can hook this directly up to any PLC that supports Ethernet IP, and we can run the whole shoot and match right off of the PLC. Start, stop, forward, reverse, speed, everything. And we can get all kinds of information back from the drive that gets it basically from the motor, so to speak, to display on your panel view. So this is another way to control your conveyor, but not necessary for all applications, just because it would be nice to have. Now, remember I mentioned that you may not want the conveyors to jerk when they start or jerk when they stop. They do sell something called a soft start-stop. It's kind of like a variable frequency drive, except that it ramps up to one set speed and then back down, ramps back down to off. So it gives you the ability to start it and slowly bring it up to speed and then slowly bring it down to a stop. Okay, object sensing. Now with the sensors on the cylinders, we sense the piston position, or if you use proxies or photo eyes out on the machine, you can sense the position of the fixturing moved by the cylinders. Now we're talking about object sensing, and the oldest and most conventional is through beam. You have a emitter and a receiver. Now I just happen to notice that this graphic, and I didn't make this graphic, I just snagged it off the internet from a good company, but notice that both electronic devices say emitter on the sides of them. We'll just ignore that. The emitter is on the left side, so one is a light source and the other is a light receiver. So if an object blocks the light, then the receiver going dark indicates that there's an object there. Now this light can be modulated. In other words, the emitter can put out a certain frequency of light. That way the receiver can't get confused between extraneous light in the workspace and light actually coming from the emitter. So this is through beam, and this is probably the most deterministic of the choices for optical sensors. This one is retroreflective, and in a way it's a through beam, except that you have, instead of a transmitter and receiver or emitter and receiver as separate electronics, they're all in one little component, and it emits light and it bounces off a reflector on the other side of the field of observation, and then that reflected light comes back to the receiver. And to make this more efficient, more efficacious, more effective, that reflector may be mechanically, the reflective surface altered in a way that the receiver, part of the sensor, can discern between light reflected from the reflector and light from some other source in the room. This is retroreflective. So you have to position the sensor and the reflector appropriately so it works when you pass the object by. And then, of course, the last one, the easiest one to install and adjust, is the diffuse reflective sensor. This senses light that is diffused off of the sensed object. If there's nothing there, then the light just goes off into space. If there's something there, it reflects light off of the surface of that object, and it's diffuse at that point, meaning scattered, and then it gets back to the receiver if there's an object there. And of course, the one drawback to this is the surface of the sensed object. If it's black, that's a challenge. Even if it's highly reflective, like polished aluminum, that could be a challenge, because if it's at a bad angle, then the light doesn't get reflected back to the sensor. Okay, object sensing. Your three choices: through beam, retroreflective. So when you see retroreflective, think reflector. When you see diffuse reflective, think reflecting off an object. This is what a through beam looks like, these little Omron components. Those two together make one application. So the red LED is your emitter, and the other one is the receiver that has the orange light and the green light. Orange says there's power, and green says it sees something. The other two could be retroreflective or diffuse reflective, because both of them have the emitter and receiver in one electronic enclosure. And we really don't care. These are just images so you can see what they look like. This is a barcode reader. The reason I'm showing you this is our virtual machine has a barcode reader on it. Now, the barcode reader is only there to kind of complete the picture. And the only thing we're doing with the barcode reader is simulating triggering it. Because remember, with our application, the barcode value tells us whether or not that part needs a whole board in it or not. If not, then it goes straight on through and out the bottom. If it does, then when it gets to PE2, cylinder 2, pushes it in to get a whole board in it. So the barcode reader is not highly functional in our application, but here's one anyway. Now, some of these barcode readers can read horizontal or vertical or in a full 360 degrees. It just depends on the design. This looks like a one axis only, meaning that it scans up to down. So for our application, it would probably be laid on its side so it was reading horizontally, the laser scan. And everyone's done enough with barcodes, like at the gas pump, you hold up your card and you can see the laser scanning across it. Barcode reader, and it has a trigger. Something needs to trigger it. In our case, that's photo I1. So here we are. New part interrupts the optical path of PE1. Barcode scanner scans the new part for boring or not to bore or not to bore. That doesn't sound like a technical phrase. Barcode indicates that boring is required, which means when the part gets down to PE2, we need to push it off into the boring station. So there it is, arriving at PE2. And because we already told our controller that this part needs bored, then cylinder 2 is poised, ready to push it off and clamp it into the boring station. We also bring out stop number 1 because cylinder 2 is extended, and we don't want another part coming down that conveyor and then resting against the rod of cylinder 2. Okay, so we extend stop 1 to isolate the new part, and when prox 4 sees the end of stroke, then cylinder 2 extends and clamps the part into the fixture. When prox 2 of cylinder 2 end of stroke is sensed, it knows the part is clamped. Energize the drill motor, and then start an at-speed delay. Now you could have started because you knew you were going to push the part off, you could have started up the motor earlier. Remember that we don't want the drill bit to hit the part before it's up to speed. Because remember, what's at play here is the inertia of the armature. So and that's why the armature doesn't come up to full speed instantaneously, is because it has inertia. So it has to overcome that inertia, gets up to full speed, and now you've got stored energy in the kind of the flywheel of that armature behind the drill bit when it hits the surface. So it gives it an extra bit of torque as it starts to torque its way into that surface with the leading edge of that drill bit. Okay? At some point, that drill bit is going to be all the way into the part and into the center cavity. Now we're going to know that because we extended cylinder 4. I got ahead of myself a little bit. Okay, the delay was complete to get it up to speed. We extended cylinder 4, and now prox 5 into stroke says it's all the way in there. But we're going to leave it in there a little bit. So we're going to start a delay to clean the bore. In other words, to auger out the debris. And once it's out and the delay is complete, then we retract cylinder 4. And we know cylinder 4 is retracted because prox switch 6 says so. And we leave the bit spinning. In other words, we leave the drill motor on because the drill bit will cool faster with forced convection than natural convection. In other words, the flutes or the blades, if you like, on that bit act like a centrifugal fan in a sense, and you get better air circulation on the drill bit. And if you're doing high volume production, then you're probably going to leave the drill bit and the drill motor on most of the time. But that's part of your programming. Okay, so we've retracted cylinder 2. And now when cylinder 2 hits into stroke, that way we know it's totally out of the way, we're going to extend cylinder 3 to transfer the finished part out onto the finished product conveyor. Prox 8 tells us that cylinder 3 is at end of stroke. We start a delay for accurate positioning. Now let me explain. That Prox 8, when you adjusted it, everyone's going to adjust it slightly different. So we want to make sure that cylinder 3 has come to a rest with that part out on the conveyor. So we add a little delay. Once you see Prox 8, we add a little delay just to make sure it's fully extended and settled. And then once the delay is finished, we retract cylinder 3, and the part is out on the conveyor. And once we've retracted cylinder 3, and PRX7 tells us that, we can start the finished product conveyor. Now, conveyor 2 goes off to the right, which means it's going downstream to another machining cell, or it's going to packaging or someplace else. But it's downstream board parts, downstream. If they don't want the part, then we're most likely going to bring out stop 2, and then when the part hits PE5, we're going to turn off the belt, turn off the conveyor, because we don't want the conveyor rubbing the bottom of the part and scuffing it. So there it sits, one part finished and ready to go. Now, and of course PE5 had to be clear, and then we extend cylinder 5. I kind of skipped by that, my bad. Now, once we hit cylinder 5 into stroke, we know everything's settled in position. And we would energize the finished product conveyor. I kind of said this backwards, so I'll back up and do it correctly. Retract cylinder 3, then if photo eye 5 is clear, we extend cylinder 5, and when it reaches the end of stroke, then we start the energized finished product conveyor, and the part moves from PE4 over to PE5 where it's at. So my illustration's slightly amiss here. That part should not be over to PE5 until after we energize the finished product conveyor. Now, once the downstream cell, whatever's off to the right, calls for parts, then we retract stop 2 and energize the finished product conveyor to move it off down to the next conveyor. In the meantime, we had a part show up, barcode scanner, photo eye 1, and because we weren't really done yet, we kicked out the stop to hold it there until we're ready for it. Okay, so we had a downstream call for parts, we retracted cylinder 5, and then we energized the finished product conveyor to rinse it out of the system, or to send it off to the right. Then we release stop 1, pull it back, and it pulls it down into position. So when it breaks PE2, photo eye, we can do it all over again. Station ready for next part, retract 1. At end of stroke, then we're ready to go. Now, what I've got here is, here are all the places that a part could be in the system. Now, you wouldn't have all these parts at the same time. I'm just showing you something to consider. So you could have one at the barcode scanner. You could have one sitting on stop 1, but not both. It's either entering PE1 or it's against stop 1. You can have one resting, or you can have one moving into photo eye 2 optical path, or you can have one passing on through on M1, conveyor 1. And you could have one at PE3, in other words, in the boring station, waiting to get bored, or finished bored, waiting to get pushed out by cylinder 3. Then you can have one at the entrance of conveyor 2 that just got pushed out by cylinder 3. And you could have one that's traveled down to the stop and is resting there at PE5. And you could have one that's on its way out. So here are 8 possible locations for parts, but they won't all 8 be there at the same time. Notice also that in the diagram in your book, the illustration, and here, I show PE3 and PE4 are optional. And that you could, as well as PE3 and 4, you can make an argument for adding more sensors at stop 1, the X of the conveyor 1, and the X of the conveyor 2. Now, in our lab project, we're going to use code to say there's one at PE3 and to say there's one at PE4. So I'm going to show you how to use logic to create virtual sensors, because machine builders are famous for getting rid of as many sensors as they can. In other words, if you can do it with logic, they figure your time is cheap and logic is free.